Now we have to deal with the obvious question. How can Cinquepetra make claims that they can produce unlimited amounts of free energy? Torque is the only requirement to make a motor spin, and generating torque is as simple as making a rainbow with a glass prism. We don't use glass prisms because we are dealing with magnetic flux instead of light. Our prisms are made of steel. With flux, we have the distinct advantage of being able to infinitely control refraction index ratios by changing the percentage of iron powder in epoxy mixtures. We can easily bend flux up to a critical angle of 21 degrees. It may not be coincidental that the critical angle for creating rainbows is about 42 degrees, or double the critical angle for magnetic flux. It's all about bending flux, or more technically, changing the direction of force vectors. Toy gyroscopes produce huge amounts of torque in a purely mechanical reaction. Unfortunately, gyroscopic torque is produced in a plane that makes it useless except for toys and guided missiles. Motors are electromechanical devices with an electro part and a mechanical part. The electro part conserves energy and has stood the test of time. Cinquepetra hypothesized that something different might be a good idea, and the mechanical part is the only thing left. Right away, the hypothesis has some merit. Rev up a toy gyroscope and twist it against the torque it produces. It does not slow down, but it consumes energy anytime the spin axis is changed even a few degrees. The energy consumption puts nuclear warheads in trash cans thousands of miles away, but the reaction being irreversible is dogma that has also withstood the test of time. Cinquepetra's hypothesis accepts the dogma, but asserts that the principles may be applied to other mechanical technologies. Asynchronous motors may be the only alternative technology where the principles can be applied. Synchronous motors require switched voltages and current, which inherently make them primarily electrical rather than mechanical devices. Asynchronous motors exhibit either slippage or torque that is independent of angular position. Tesla's AC induction motors inherently have slippage, causing slight speed changes with increasing load, and classical DC motors produce the same torque regardless of where the wires are situated in the stator field. Fortunately, the two examples are the same. When viewed from a mechanical perspective, laminations from the two examples are hard to differentiate, and in fact can even be interchangeable. With just a little simple logic, Cinquepetra's hypothesis is narrowed to a single mechanical reaction. Motors are described in many ways using many frames of reference and just as many terminologies. Rotating field is a good term, but back EMF is the inventor's favorite by far. The inventor feels he has earned the right to create a new terminology, and stimulation is very easy to understand. The concept merely recognizes that Faraday forces in motor air gaps are perpendicular to magnetic attraction forces from stator magnets. The perpendicular forces are independent as vectors, but the total reaction involves redirecting the attraction force by increasing or decreasing the air gap energy. Current carrying wires are active elements in a magnetic circuit and add energy, while passive elements only diminish the air gap energy. At last we have some pictures. First, we have a classical representation of a motor: stator, rotor, and wire. With no current, the attraction is a radial force. No torque, no spin. When a current is applied, the attraction force and energy are obliquely vectored, producing torque, and the motor spins. Let's look at the difference between active and passive stimulation. With electrical stimulation, the energy increases. With mechanical stimulation, the energy decreases. It makes sense. With mechanical stimulation, there is no way to add energy. Some of you might see the trend. What's missing is the gyroscope, and its stimulated vector would be constant energy and fall along the constant energy curve. So, how's it done? Start with a solid steel bar to find E0. Chop away the parts of the bar that increase torque. When chopping doesn't work anymore, mix up some epoxy with iron powder and fill in the spaces that increase the torque. Iron filings work much better, but they are hard to find and they need to be magnetized while the epoxy is curing. You might be wondering if we will help you steal the technology. Sure we will. Go to a yard sale and buy 60 or more low-quality Alnico long bar magnets like the ones used in grade school science classes. They are not very powerful, but neomagnets have worse problems. You will also need a diamond saw tile cutter from Home Depot. Make the asymmetric magnet motor shown on YouTube. You'll need to do a little work to find out the right lengths and angles. You might need a few more magnets. If you run out of magnets, you might try this with one of the skewed electromagnets attached to a pendulum. Very tight, small wires work the best. Getting the wires close to the surface and parallel is critical. When their line is shown, you'll know you are close. Then play with different areas. It will really help with the magnet motor. With the right areas, start changing the surface angles and filling the spaces with epoxy steel prisms. 52% by volume work best for me. That's about 80% by weight. Apply extra so you'll have material to file away. Once you have your prisms and steel right, separating them from the magnets will give you all the free energy you could want. You'll be spending a lot of time at the computer and in the lab, so you might want to consider spending some time at the gym when you're done. But remember, Vilma Cinco doesn't like people trying to steal her stuff. The bottom line is the same as the top. Torque is the only requirement to make a motor spin, and generating torque is as simple as making a rainbow with a glass prism. We would appreciate any input, feedback, criticism, or even more if you could tell a few friends to look at this video. Thank you very much.